Welcome back. Today we'll talk about data fitting and in particular interpolation. One of the things that computers are particularly valuable for is handling data, particularly handling large amounts of data. Obviously in our lecture here we'll keep the amount of data small since I can handle them, but in a real world you can handle very big problems. The problem now is one you may have seen in high school or elementary school even, is if you have a table of numbers, a table of data, how do you interpolate between them? You know, if you have a table, probably the value you want is someplace in between. How do you get a number in between listed entries? In another lecture, later anyway, we'll talk about how you actually do a best fit to data. And that's more of a statistical problem in which you try to incorporate errors in the problem. Here we'll just talk about interpolating numbers. So let's get on with it. Let's look at slide 2. Here's the problem. You have on the left here a table of numbers, and energy E is tabulated, so that's the independent variable, obviously in uniform steps, does not have to be uniform at all, and that's what's been measured on the meter. And then for each value of energy, another value of the function has been measured. In this case, looks like a differential cross-section. Okay? And the question is, what do you want to do with this? Well, if we look at the numbers, we can't tell very much. If you plot it up, always a good idea when looking at data to plot up either all of it or at least some of it. You have the computer tools to do plotting, very good to visualize. So what you see here is, oh, the data are fairly smooth, they look smooth, they're increasing. Good. And what we'd like to do is say, what if I need a value someplace in between, like here? How do I get it? What's the best value could be? Okay. And that's what interpolation is. And what it does in a more abstract sense is if we have some formula we can use that interpolates all these data, lets us effectively draw by hand here or on the computer, lets us draw a smooth curve through the data, we can take what was a table of numbers and convert it into an analytic function which we can just use in our equations. Okay? And then as your exercise is to determine where the peak in this cross-section occurs, whether it's here, when you fit it with a polynomial of some sort, whether it shifts a little bit, and what's the full width at half maximum. So if you go down to half the value, around 40 odd here, you know, what's this width to some precision. So that's what we'd like to do from these tables of numbers. So now let's look at slide 3, which talks about how you actually do a polynomial fit. So equation 1 on slide 3 here shows you a polynomial. The order of the polynomial is n, which means here if we have powers up to, I take it back, the order here is n minus 1. This is a polynomial with n coefficients. So the counting starts at 0, so this is order n minus 1 polynomial, which means n points. So often in fitting you talk about an n-point fit. So if you're using n points, for example 2 points to fit data, that's a straight line, which is x to the first power. You use 3 points, 1, 2, 3, that would be a cubic. No, that would be a parabolic fit with 3 parameters. So one of the points of confusion. Case well taken right here. So we'd like to fit data with polynomials of this sort. And up above here we have some sample fits to those same data I've showed you using different kinds of polynomials to fit it. So what's the lesson here? Well, the lesson here is this: you can be too clever, you can do too good a job, and then end up with what's scientifically unreasonable. You want to keep all your polynomial fits local. And that means in each region, say here to there, in the middle, we're going to have 3 points. We may fit a cubic or just a parabolic function to these 3 points, and then another parabolic function to this other region, and then another parabolic function there, and we keep it local. You could say, hey, that's a lot of extra work. Why don't I just get it all done in one fell swoop? Why don't I just fit all 9 points with one polynomial? 9 points would be an 8th degree polynomial. Well, that's what happens here on the left. And what you see is, hey, if you tell a polynomial to go through every data point, it does. But it's a high degree polynomial, and they're known for oscillating a lot. And what you can see is, ooh, there's an oscillation here between the points and at the end, which nature probably does not have. Now, it may have. You can argue, how do we know what nature is? And the answer is, well, I don't know just from a table of numbers, but a good scientist, a good engineer would be conservative and say, let's not put more in than we have to. And so we want it smooth. So a high-order polynomial can give you unrealistic oscillations, or at least probably unrealistic oscillations. Another type of fit which we'll talk about, and that's the smoothest possible fit you can make, is called a spline fit, and we see that here as well, and it's very, very smooth. It's always very, very smooth. If it shouldn't be smooth, then you don't want a spline. Okay, so before we leave, we should mention what's a perfect fit here. Well, that'll get us into our next lecture as well, but a perfect fit is not necessarily one which goes through all the data points. This polynomial is a perfect fit, goes through every data points, but if the data has noise, or if it's not really a polynomial, which this is not, it's not a perfect fit in a scientific sense. So be careful. In particular, the one word you never want to even hear is extrapolate. Now, you can use these equations to extrapolate. In other words, you can use them to predict what the data will do after the table. But then there's no data points to hold it down. So this function may go down here someplace crazy. This other one here may go up there, and it's unreliable. So that's not scientifically what you do. So look at slide 4. Slide 4 talks about an endpoint Lagrange interpolation, which again, endpoints means n-1 degree polynomial. Well, Lagrange was rather a genius, one of these mathematical geniuses, and he could do things which ordinary people could not. He said, I have this problem, this guy Landau assigned to me, how do I write a closed form solution to it? And he did it. So he said, if I want endpoint in a table to be fit by an n-1 degree polynomial, here is exactly a closed form expression for what that polynomial must be. And that's what's equation 1. So what you see in equation 1 is you see f1. f1 is just the first value in the table. f2 is the second value. f3, etc. f sub n here is the nth value. In this case, we only have 4. So these are just, f's here are just the values in the table, and each lambda is a polynomial. And Lagrange wrote the polynomial down as the product. And these are all known. X is just a variable, so you can use this equation to give you the function at any value of x you want. xj is just one value in the table. xi and xj, again, are values in the table. So this is just the product, as written out in equation 2, of unknowns x that you want to interpolate on and the values in the table. That's it. So it's a closed form expression. It's kind of messy to look at there, but trivial to program. In fact, the product is just a simple do or for loop. Very easy to program. So let's look at an example of this. The example is, we have 4 points in the table. What can we fit 4 points with? 4 points, third degree polynomial. Okay. So how do you do it? We do it right there. We just apply equation 1, and what you see here step by step is, first we have minus 12. Well, minus 12 is just the value of f1. That's right, it's in the table. There's f1. Then we have another minus 12 here in sort of a triangle. That should just be the value of f2, which it is. There it is again. And then we have minus 24, which is the third, and we end with minus 60, which should be the last value it is. So those are just the values of the functions, and then we just have, it's going to be a cubic because n is 3. Okay, n is 4, so we have from 1 to n in this case. Okay, so we're starting off at x, we get another x, we get another x, we get a cubic polynomial. Each of them has similar top, but it's x minus x sub j. J, we're just running over the values in the table, and that's each polynomial. So you get some algebra to do if you do it by hand. If not, just leave it like that for the computer. But if we do the algebra by hand, we get, there it is. That's a cubic. So that's the cubic function that fits this table. As a check, we can evaluate it at 4, which is one of the table values, tabulated values. We get minus 60 as the answer. It works. So, to repeat, this is a closed form expression, trivial to compute. It'll always work. Don't use it for n too large, but n is too small. It works very well. Okay. The next method of interpolation, and the one which is very popular, is called cubic splines. Look at this cubic we have given you here. If you look at it, you realize, oh, that's a nice, interesting way of writing a cubic, isn't it? F sub I are still the tabulated functions, except values we have. And now what we're doing here is we're saying in each region, region I of the table, which is near point x sub I, we'll have one cubic. And the cubic will have, to start with, the constant will just be the value in the table. Fi sub 1, this is just the first derivative, that's prime. Fi sub 2 is just the second derivative, double prime. And F sub 3 is the third derivative. And then these are just x minus, these are just the polynomials. So we've written the cubic in terms of the derivative of the function. So here is the technique. Okay? So we always, when you do cubic splines, will always fit a third degree polynomial in each interval of the table. So between every two tabulated points, we'll fit it with a third degree polynomial. And you might be saying, you can't do that. He just told us on the slide before, we're not that dumb, we don't forget that quickly, that if you want to fit a cubic, you need 4 parameters. Well, 1, 2, 3, 4, you're right. Even it says up there. So the way you do that is you say, okay, we'll fit a cubic in each interval, and it'll be a different cubic, but we'll guarantee that the first and second derivatives are continuous. And that gives us more equations. And what you see here is it's very eye-pleasing. What we end up with, what you see is right here. For example, I just drew this curve here. That's just a bunch of points connected with splines. And it's always smooth. It's always very nice looking. Okay. Do you remember the name spline? You may have heard it before. Do you know where it comes from? Well, it comes from a flexible drawing tool. So here, for example, here's a spline. Okay. It's flexible. It's a tool. We can straighten it out, make it straight, and we can use it for drawing. And you know, this is where it comes from. So, okay, so let's do a real demonstration of a spline. So here we'll have our table of numbers. I don't see a table of numbers. Well, let's put some on. Let's say this is the table of numbers you're given, and we want to draw, do a spline fit to them. Well, here's a spline. I just take it, I bend it till it fits, then I hold it in place with a third hand that I wish I had, and then I just draw a smooth curve through it, and lo and behold, I get a spline fit, pardon me, to these data just fine. Okay, so here's our spline, and this is, you know, that's where it comes from. How do we do this mathematically? Well, the answer is it's not very hard, but it is tedious. Okay? So when we're done, however, when you fit each little interval with a cubic, you end up with a function that is guaranteed to be integrable because it's just a continuous function, and continuous first, second, and third derivatives will be integrable. It's also differentiable, and that's very important because sometimes, for example, if that's a potential function in physics, you know the force is the derivative, so you can use your fit value to the table to deduce higher derivatives, and they'll be quite reliable. You won't have any singularities in them. Okay? As you see here, it's very popular for graphics. It's usually any drawing program, any graphics program on the computer that has a smooth curve is a spline fit. You should try this yourself, and we give you 2 ways of doing that. We have on the CD both an application, which is a regular program in Java, and an applet, which runs from a web browser, showing splines. And you can look inside either of them, which is often very educational. So here, for example, this should be, here's our spline applet. And what you see here is the same data points we're trying to fit, and you can adjust the number of points you want fitted. So if it's just 3 here, what you see is here in a little green dot, another little green dot, we've just distributed 3 points equally. But if you say, let's distribute 300 points, 300, enter, aha, it's just put lots of points through, and you can see that's perfectly smooth. It'll always be perfectly smooth. So let's go back. You should try that on your own. You can try some drawing programs and have it work as well. Okay. So here, how do we actually implement splines? Well, I will show you that if we look now at slide number 6. Okay. So equation 1 is again our cubic spline function that we're using, one of these in each interval. And now the first thing we need to do is to say we need to match f sub I, in other words the value of the spline, which is the cubic, and for each adjoining interval. So the intervals that overlap, adjoin, have to have the same value of the function. So that gives us an equation, equation 2 here. The ith spline at the end of its interval, which is at point I plus 1, must be equal in value to the I plus 1th spline at the beginning of its interval, which is x to the I plus 1. If you think that's easy to say, try it, okay? So that's equation 2. That gives us a whole set of equations from I equals 1 to n minus 1. Okay, so we have n minus 1 equations. Likewise, we now require that the first and the second derivative at adjoining intervals also be continuous. So that gives us equation 3. So for the end of interval I minus 1, so that's the end point, must be equal to the derivative at the beginning point of the next interval of I. And likewise, the first derivative, the second derivatives also must be continuous. That gives us another set of equations. And then we want the third derivative to be continuous. And we require that in the simplest way, just with a forward difference derivative. That gives us equation 4, which is, and that's the equation for the third derivative in terms of the previously evaluated second derivatives. So this gives us a whole bunch of equations, and you think, boy, that's more than enough equations for anything I want to do. Certainly, this is the reason people couldn't do this by hand. Just too many equations when n can get to be hundreds, and they're a nuisance to solve, but it's actually not enough equations. You need something more, and it's usually the boundary conditions that give you the necessary conditions. And you can either input the values of the derivatives at the boundaries, the second derivatives, or you could say, let's use the natural spline condition. So here's a spline. What's the natural conditions? Well, there's a slope at the endpoint, so the first derivatives don't vanish, but there can't be any curvature at the endpoints because there's nothing on the beyond the ends to hold it or bend it up. So a natural spline is like the one in my hand. The second derivatives, the curvature, vanishes at the endpoints. And that's all there is to spline. That's the equations. They're not hard to solve. We do it on the computer for you. We give you a program because I've tried writing my own. It's hard to get it just perfect, and it takes time. So here, which is impossible for you to grasp all at once, but here is just some items from our spline program. Spline APPL, meaning application. As a reminder, there's also an applet. So it's just the application here. These are just the values of x and y. So that's just the table of input values. We also have to have a value for the first derivative, y prime, at the first point, and a value for the first derivative at the last point. And so here we're just calculating it in terms of the tabled values. If you know the value, even better, of the derivative, you could input that as data, get a better fit. But if you don't know it, we just calculate it. We're making it a natural spline, so the second derivative, the double prime, vanishes, and we just call it several things. And then we just decompose the equations, decompose the data. There's an initialization, and it's then just, we have all the values, we know how to solve the equations, and then a lot of the code is just outputting the x and the y values. So we're just making that table up for the plot, and that's the function. We're just using the appropriate cubic function in each interval. So that's roughly what a spline fit looks like. It's a bit of work. You have to be careful, but now we give it to you. So go ahead. Go out in the real world. Try it out. See how beautiful it works and how limited it is if you have noise in the data, because you don't want to fit the noise. But we'll talk about that next time. Bye-bye for now.